Hello everyone, here's another Physics 30 example set. This time we are into Unit 4, which is Electromagnetic Radiation, or EMR, and this is example number 1. We're back into the wave equation, so here we have our Physics 20 stuff coming back to be used. One difference here, of course, is that we're using light. So rather than it being a wave through some other kind of medium, this is a wave made from, or it's a wave of EMR. And so we know that there is a known constant velocity. And if we're talking about the velocity in air, or essentially in a vacuum, we can go ahead and say that the velocity of the wave is equal to c. And that is a known value that we'll call 3.0 times 10 to the 8 meters per second. So we know the speed. Here we have a little image of a transverse wave, or a sinusoidal wave, I guess, if you want to call it that, traveling along a distance. So we have to imagine this as being an oscillating wave, and if we were to follow one of the peaks, it would move along this distance here, which is given in nanometers. And we're asked to find the period of the source vibration. So of course, to make this wave oscillate along in a direction, there would be a source vibrating up and down like this. Okay, and actually that's how radio works. To produce EMR, all you have to do is accelerate a charge. And so in the aerial of a transmitter, a radio transmitter, all we need to do is move a current. We need to jiggle it up and down, and that's going to essentially oscillate electromagnetic waves away from the source. What we need to do here is find out the period. In other words, how long it takes one full wavelength to pass a given point. So let's take a look at the picture. We're dealing with single wavelengths, so I'm just going to break this up into an individual wavelength. Hopefully you can see that this is a wavelength here, and this is a wavelength here. So this total distance, this distance here, which is 800 nanometers, is equivalent to 2 wavelengths. Okay, so that's pretty obvious that the length of a wave is going to be half of this, so it's going to be 400 nanometers. Okay, well, maybe we'll need this at some point. Okay, other things going on. Well, we also know, well, we've got the speed over here, but we also know from our Physics 20 that we know that if there's a wave and it has a speed, or I could probably just put it as a speed, if it has a speed, then the universal wave equation tells us that it's a product of the wavelength and the frequency. Okay, but we're asked to find period. So the other thing that we're going to need is that the period is the inverse of the frequency. And hopefully this means that, hopefully you can see this, that when we combine these two together, we can say, so I'm going to go therefore, this case the speed of light, which is a known value, okay, is going to be equal to the wavelength multiplied by, actually let's do it like this, multiplied by the inverse of the period. Okay, and so I can simplify that and just say wavelength over period. Okay, hopefully that's clear. And so from here it's pretty straightforward. I'm just going to rearrange this to solve for the period. So period is wavelength over the speed of light, and if I go ahead and put that in, I'm going to get, I might as well put the values in. I've got 400 nanometers. Well, nano is times 10 to the 9, it's a billionth, over the speed of light, which is 3.0 times 10 to the 8 meters per second. Sorry, speed of light in a vacuum, or speed of light in the air, which we're assuming is the case here. And that's going to give us our period. And if you plug it into your calculator, you get 1.33 recurring times 10 to the negative 15. Oops, 10 to the negative 15 seconds. So really quick, what that means is that the time it takes for one full wavelength, So this full wavelength to pass a certain point is 1.33 times 10 to the negative 15. It's really quick. How quick? It's light speed quick.